Hi guys, again Pranav is here. Today I am going to explain hydrogenerator part 20. All other links of the previous parts are given under the description box. For sustainable operation, since hydroelectric generators can have to undergo start or stop almost instantly, so hydropower is much more responsive than most other energy sources for meeting peak demands. Moreover, hydroelectric generators are also ruggedly designed to have a quick response with ever-changing system conditions, such as to rapidly varying loads or system disturbances, which base load plants cannot be readily accommodated. Equipped with best possible sophisticated technology, the efficiency of today's hydroelectric plant is about 90%. The main control and automation system in a hydroelectric power plant are thoroughly associated with the required transmission grid system regulation, having with supply and demand balance, supply of reactive power and voltage control, frequency regulation, and support, stability, and black start capability. Hydropower has the flexibility to rapidly ramp the generation up and down in response to changes in the balance between the electrical loads. Hydro plants are mainly using as peaking power plants, typically operate for limited periods of extremely high demand period. As for example, these plants often provide high output during the day and lower or even zero power levels at night. Elements to be controlled for sustainable operation of hydro generator. There are several elements from which the important elements are: one, intake gates, that is where from the water is coming out, main inlet valve, then turbine, governor system, lubrication system, excitation system, generator circuit breaker. Now, intake gates and main inlet valve both are associated with the following points. That is, both are responsible to make the running system inoperative and conserve water during shutdown of the plant. Turbine and the governor. Governor has to control the turbine gates so as to regulate the water flow in the runner in proportion to the load requirements of the turbine. Lubrication system has to establish a lubricating film on the bearings during starting, maintain it during operation, and circulate the lubricant so that it can be cooled. Excitation system. Number one, excitation system equipped with AVR, that is automatic voltage regulator, so as to control the voltage requirement and demand for reactive power output of the generator. Number two, generator field circuit breaker provides field interruptions during faults and thereby minimizing damage to the generator and other equipments. Last one is generator circuit breaker, which serves to connect the generator to the grid system for delivering power and disconnects the generator from system prior to shutdown or experiencing any electrical fault. Abnormal operating conditions. Over and under voltage in stator winding might have been due to loss of synchronism, that is out of step. Machine is in out of step. Overloading condition, there is loss of prime mover, there is motoring. Abnormal frequency over and under, therefore vibration. Loss or insufficient field excitation, that is due to sub-synchronous oscillations, sub-synchronous resonance. Overexcitation, overrating of bearings, unbalanced current, ventilation failure, inadvertent energization, and blown VT fuses. Again, I repeat, abnormal operating conditions, over or under voltage in stator winding, loss of synchronism, that is out of step, overloading condition, loss of prime mover, that is motoring, abnormal frequency, over or under, any sort of vibration, loss or insufficient field excitation, sub-synchronous oscillations or sub-synchronous resonance, overexcitation, unbalanced current, inadvertent energization, overrating of bearings, ventilation failure, blown VT fuses. These are all the abnormal operating conditions. Now, what is sub-synchronous oscillations? That is sub-synchronous resonance. The series capacitor compensation technology is being the widely used method of improving the system voltage by adding capacitors in series with the transmission line. The main purpose of connecting capacitor banks in series with the transmission line is to decrease or compensate the reactive impedance of transmission line to reduce voltage drop over long distances so as to put some restriction on the Ferrante effect by increasing the voltage at the point of connection. Number 3, restriction of voltage drop across the line with more compensation that allows to improve the load transfer ability of the line up to its thermal capacity, resulting more power to be received by the load side for any given sending power. This technology provides an improvement in grid stability for bulk power transmission and also has contributed an optimal utilization of long EHV and EHV, that is extra high voltage and ultra high voltage transmission lines. However, the use of series compensation may have to trigger some new problems to power system operation. Series compensated line produces series resonance at frequencies lower than power frequencies and is known as sub-synchronous resonance. Potentiality of sub-synchronous resonance may lead to the torsional oscillations of turbine generator shaft system. Possibility of breaking turbine generator shaft could be an outcome of an accumulative process of the torsional oscillation for either a long time having slow amplitude or a short time having high amplitude. Subsynchronous resonance, though it is a very serious and critical phenomenon for the turbine generator shaft failure, but still it is identified as a rare instance to encounter. Resonance between synchronous machines and the electrical grid may occur for frequencies other than fundamental frequency, that is 50 Hz. Electrical grid has always to be contained with series capacitors, and for which natural resonances in the grid would have been imposed for subsynchronous frequencies having with the nature of series or parallel resonance. That is, the inductive and capacitive grid elements can either form a series resonance circuit or a parallel resonance circuit. These subsynchronous resonance frequencies of the electrical grid, while just to coincide with any of the mechanical frequencies of the turbine generator shaft, then a torsional interaction may appear, which is referred to as subsynchronous resonance or oscillation. If the electrical damping for a specific frequency in the connected electrical network is not adequate as compared to the mechanical damping of the operating synchronous generator, then that frequency may lead to have a mechanical stresses or even failure of the turbine generator shaft. However, during oscillations, the generator will have to be exposed to frequencies, both subsynchronous and supersynchronous of the nominal frequency. Nature of fluxes as developed due to these frequencies will then start to induce different level of voltages as corresponds to frequencies, resulting a fluctuation of currents in the grid. These fluctuating currents are caused by the existing impedance of the connecting transmission grid, including generator winding part also. These currents with sub and supersynchronous frequencies will thereby interact with the nature of sub and supersynchronous fluxes, causing to develop torques that can either damp or amplify the mechanical oscillations. The total torsional damping may have to initiate from subsynchronous electrical damping, the supersynchronous electrical damping, and the mechanical damping. Let's repeat again. The total torsional damping may have to initiate from subsynchronous electrical damping, the supersynchronous electrical damping, and the mechanical damping. These three quantities are responsible for total torsional damping. It is to be concluded that the subsynchronous resonance is really a critical problem in the power system, and especially the series compensated transmission lines are responsible for subsynchronous resonance in the turbine generators, which leads to the electrical instability and potential turbine generator shaft failure. Perspective of generator grounding. The stator winding construction of high power rating large synchronous generator has always been configured with transposed rowable bar in order to suppress losses caused by eddy currents and circulating currents. Transposed rowable bar has already been discussed in the previous slides. So, failure of insulation is more likely to have a result due to the winding to ground fault than in a face-to-face fault. Other failures, such as broken conductor or interturn fault, normally may not be detected until the fault has rather to be extended into a winding to ground fault. For generators, stator earth fault protection is one of the most crucial protections, and the protection scheme is, however, dictated by a great extent upon the type of generator grounding. Generator grounding is necessary, keeping the basic objective to follow is that the higher the magnitude of the grounding impedance, the smaller will be the magnitude of fault current. Again, if the magnitude of the ground impedance is considered to be high enough, then the phenomena will be difficult to differentiate between low magnitude fault currents and harmonics. So, priority must be given to establish a better coordination in order to function all the protective relays as per necessity. In order to restrict the magnitude of the fault current, at least low impedance grounding through a resistance or a reactance is meant to be implemented. Most common grounding configuration for generators is to provide high impedance through a distribution transformer whose primary winding is connected between the neutral terminal of the generator and ground. The resistor, neutral over voltage relay 59N, and third harmonic neutral under voltage relay 27TN are connected in parallel across the neutral grounding transformer secondary. While the fault develops very close to the generator neutral, the over voltage element will not pick up because the voltage level will be below the voltage element pickup level. Though a low value grounding resistance connected between generator neutral terminal and ground provides better grounding source. But at the same time, lower value of resistance causes more damage to the generator windings on internal ground faults. For generators with unit transformer, that is generator transformer, and with high impedance grounding of the neutral, then a neutral voltage relay having with harmonic immunity and of independent adjustable time delay has to be provided for better way of protection. The neutral voltage relay is fed either from a neutral voltage transformer or from the broken delta winding of three-phase voltage transformers, which is on the generator line side. This is the diagram. One is low impedance grounding, another is high impedance grounding with 51GN and 51N. IEEE function number for generator protection relay. IEEE number 24 is overexcitation, 25 synchronism check, 32 that is reverse power single stage, 32-1 reverse power and non-electrical trip supervision relay, 40 loss of field that is due to bar flow approach, 50 by 51N stator ground overcurrent, low medium impedance ground neutral city of flux summating city, 51GN 51N stator ground overcurrent high impedance ground, 51 VC voltage controlled overcurrent, 51 VR voltage restrained overcurrent, 59N 27-3N 59P all are ground over voltage. 46 negative sequence overcurrent relay, 49 stator temperature that is RTDs, 50 or 87 differential via flux summating city, 50 and 27 IE inadvertent energization overcurrent with 27, 81 supervision relay, 51N stator ground overcurrent, low medium impedance ground phase city residual, 67 IE directional overcurrent for inadvertent energization, 81 over or under frequency, 87G generator phase differential, 87N generator ground differential, 87 UD unit differential. Design and engineering philosophy. Technological upswing in designing better cooling arrangement, introducing advanced phase of insulating substances as well as having major breakthrough in metallurgical configuration of magnetic materials, applying fast response, digital governing and excitation systems. The hydrogenerators in present context of higher rating with lower weight ratio have been developed. And it is rather available in the market. However, selection of hydrogenerators are generally be of tailor-made to the specified site conditions, that is, available internal area dimension of the machine floor, and accordingly, the manufacturer has to proceed for inquiring the availability of sizes, variety, and complexity of various machine tools, logistical limitations involved in site implementation, etc. Combination of water head and capacity are also be the prime consideration for the selection of the hydro turbine and generator, both. I repeat, combination of water head and water capacity are also be the prime consideration for the selection of hydro turbine and generator. The possible site-wise combination of water head and capacity and other factors are always be so much different that identical units can hardly be implemented at more than one site. It is an important phenomena. The possible site-wise combination of water head and capacity and other factors are always be so much different that identical units can hardly be implemented at more than one site. That is the reason for which tailor-made generator and turbine is required. As the construction of hydro projects are always being site-specific, so selection of turbine has also to be made by considering the specific water head and output. Selection of turbine is to be decided so that it may fulfill the specific conditions under which it has to operate and attain the maximum possible efficiency. One, based entirely on head and quantity of water available. The turbines can be classified: A, high head turbines. High head turbines are the turbines which work under heads more than 250 meters. The quantity of water needed in case of high head turbines is usually small. The Pelton turbines are the usual choice for high heads. Number B, medium head turbines. Medium head turbines are the turbines that work under a head of 45 meter to 250 meter. It requires medium flow of water. Francis turbine are the usual choice for medium heads. C, low head turbines. Low head turbines are the turbines which work under a head of less than 45 meter. Owing to low head, large quantity of water is required. Kaplan turbines are the usual choice for low heads. Selection of turbine entirely based on head available. Above 300 meters, type of turbine to be recommended: Pelton wheel turbine. 240 and 300 meters, Pelton wheel turbine or Francis turbine, preferably Pelton wheel turbine. 150 and 240 meters, Francis turbine or Pelton wheel turbine, preferably Francis turbine. 60 to 150 meters, preferable turbine is Francis turbine. 30 to 60 meters, Francis turbine or Kaplan turbine, preferably Francis turbine. 15 to 30 meters, Kaplan turbine or Francis turbine, preferably Kaplan turbine. Less than 15 meters, Kaplan turbine. Now selecting the appropriate type of turbine depends primarily on available head and less so on available flow rate. Three primary types of turbines: A, the Pelton turbine for high heads; B, the Francis turbine for low to medium heads; Kaplan turbine for a wide range of heads. References: one is Alternating Current Machines by MGC, Electric Machinery and Integrated Treatment of AC and DC Machines by Frizzell and Charles Kingsley. Number 3, Electric Machinery Fundamentals, second edition by Stephen J. Chapman. Number 4, Electrical Machines, Drives and Power Systems, 5th edition by Theodore Wilde. Electrical Machinery by Dr. S.K. Sen. IEEE Guide for AC Generator Protection. Thanks for the patient hearing. I have just completed the hydro generator. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for listening,